The concept of time, often perceived as a relentless, unidirectional flow, is more than just the ticking of a clock or the changing of seasons. It's a tapestry woven into the very fabric of the universe, a dimension that alongside space forms the backbone of our reality. At the heart of understanding time lies Einstein's theory of relativity, a groundbreaking revelation that transformed our perception of the universe. Time, according to Einstein, is not a constant universal ticking that affects all equally. Rather, it's relative, bending and stretching in the presence of gravity and at high velocities. This startling idea suggests that time runs differently for an astronaut in space than for someone on Earth. It's not just a concept out of science fiction, it's a scientifically observed phenomenon, verified through precise experiments like those involving atomic clocks on fast-moving planes. Physicists define time in a way that intertwines with the fabric of the universe, a concept that is both familiar and profoundly complex. At its most basic, time can be seen as a measure of events from past to future. But this simple definition barely scratches the surface of its true nature, especially when viewed through the lens of physics. In the realm of classical mechanics, which deals with the motion of objects much larger than atoms and at speeds much slower than light, time is a straightforward, constant progression. It ticks away uniformly, indifferent to the state of the universe. However, the advent of Einstein's theory of relativity dramatically changed our understanding. In this view, time is not a separate, absolute entity, but a component of a four-dimensional structure known as space-time. According to Einstein's theory, time dilates or stretches in the presence of gravity or at high speeds. For instance, clocks on satellites in orbit, where gravity is weaker, tick slightly faster than those on Earth. This isn't just theoretical. It's a practical consideration that has to be accounted for in the functioning of systems like GPS. Furthermore, in quantum mechanics, which deals with the behavior of particles at the smallest scales, time plays an even more elusive role. Unlike relativity, where time can bend and stretch, in quantum mechanics, it remains a background stage against which particles interact. The unification of quantum mechanics and general relativity, two of the most successful theories in physics, into a single theory that comprehensively explains time remains one of the greatest challenges in modern physics. Physicists also explore the possibility of time's quantum nature. This leads to speculative yet fascinating theories like loop quantum gravity, which suggests that time, along with space, is granular, made up of tiny, indivisible units. If true, this would mean that time, like matter, has a fundamentally discrete structure, challenging the continuous flow of time we experience in our daily lives. Time is considered a fundamental dimension because it is intricately woven into the very essence of our universe, playing a crucial role in the way we understand and experience reality. In physics, our universe is described as having four dimensions: three of space, length, width, and height, and one of time. This fourth dimension is what allows us to perceive the progression of events, from the blooming of a flower to the aging of stars. One of the primary reasons time is regarded as fundamental is due to its relationship with space, forming the concept of space-time as described in Einstein's theory of relativity. In this framework, time cannot be separated from the three dimensions of space. They are interconnected, influencing each other. The significance of this relationship is most evident in phenomena like gravity. According to general relativity, massive objects like planets and stars warp the space-time around them, and this curvature is what we perceive as gravity. This warping affects not only the movement of objects through space, but also the passage of time. Near a massive object, where space-time is greatly curved, time moves slower compared to areas where space-time is less curved. This effect, though minute in our daily experience, has been measured with precise instruments like atomic clocks. Moreover, time as a dimension is essential for the laws of physics as we understand them. It provides a framework for understanding the sequence of events and the causality that governs physical processes. Without time, concepts like motion, velocity, and energy would lose their meaning, as they inherently depend on the change and progression that time allows. In cosmology, time provides a timeline for the universe, from the Big Bang to the present and beyond. The age of the universe, estimated at about 13.8 billion years, is a measure of time that helps us understand the stages of cosmic evolution, from the formation of the first atoms to the birth of stars and galaxies. The fundamental nature of time also poses deep philosophical questions. For centuries, philosophers and scientists have pondered whether time is an actual dimension of the universe or a construct of human perception. This debate touches on the very nature of reality and our place within it, illustrating how time, as a concept, extends beyond the realm of physics into philosophy and human cognition. The concept of the arrow of time is a fascinating and crucial element in our understanding of the universe. It refers to the one-way direction or asymmetry of time, moving from what we perceive as the past, through the present, and into the future. This concept is more than just a philosophical musing. It's a fundamental aspect of the physical laws that govern our universe. At the heart of the arrow of time is the second law of thermodynamics, a principle stating that in a closed system, the total entropy, often thought of as disorder or randomness, tends to increase over time. This law provides a physical basis for the direction of time, illustrating why processes in our universe generally move from order to disorder. For example, consider a cup of hot coffee in a cool room. Over time, the coffee cools as its heat spreads to the surrounding air. This process is irreversible under normal conditions. The coffee won't spontaneously heat up again. This one-way flow from hot to cold, from ordered to disordered, exemplifies the arrow of time. In cosmology, the arrow of time has intriguing implications. The universe began in a state of extremely low entropy at the time of the Big Bang and has been moving towards higher entropy ever since. This increasing entropy defines the direction of time at a cosmic scale. It's what gives us a distinction between the past, the highly ordered state of the early universe, and the future, which tends towards greater disorder. Another perspective on the arrow of time comes from the field of quantum mechanics, where time's flow doesn't inherently have a preferred direction. The fundamental laws that govern particle interactions are mostly time-symmetric, meaning they don't change if time is reversed. This symmetry raises questions about why the macroscopic world, governed by these laws, exhibits a clear arrow of time. The reconciliation of this discrepancy between the microscopic and macroscopic worlds remains an area of active research and debate in physics. Is time's forward movement a universal law? The notion that time always moves forward, never backward, is deeply ingrained in our everyday experience. This forward movement of time, often taken as a universal law, is actually a subject of considerable debate and study in physics and philosophy. While our day-to-day observations affirm that time seems to march relentlessly forward, from the past through the present and into the future, the fundamental laws of physics, particularly at the quantum level, don't necessarily support this unidirectional flow. In classical physics, time is treated as a constant stream moving at a uniform rate, independent of the observer's state of motion or position in the universe. This view aligns with our intuitive understanding of time. However, Einstein's theory of relativity introduced a more complex picture, showing that time can dilate or slow down in the presence of strong gravitational fields or at high velocities. Even with these intriguing properties, relativity does not contradict the one-way progression of time. It simply modifies how we measure and perceive its passage. The real challenge to the concept of time's unidirectional flow comes from the realm of quantum mechanics. Here, at the scale of atoms and subatomic particles, the fundamental laws governing particle interactions are largely time-symmetric. This means that the equations describing these interactions remain valid if time is reversed. In this microscopic world, time doesn't have a preferred direction. This symmetry poses a stark contrast to the macroscopic world, where the second law of thermodynamics dictates an increase in entropy over time, reinforcing the one-way arrow of time. So, is time's forward movement a universal law? The answer isn't straightforward. On a large scale, in the world we see and experience, time does appear to move in one direction, as evidenced by the increasing disorder and the aging of objects and living beings. This observable fact aligns with the laws of thermodynamics and shapes our understanding of the universe and our place in it. However, at the quantum level, where the fundamental building blocks of the universe operate, time's directionality is not as clear-cut. The symmetry of time in quantum mechanics suggests that, in principle, time could move in either direction. Bridging this gap between the macroscopic and microscopic understandings of time remains one of the great challenges in modern physics. The perception that time always moves at the same rate is a cornerstone of our daily experience. However, in the realm of physics, the rate at which time moves is not a constant, but rather a variable that can change under certain conditions. This concept, which may seem counterintuitive at first, is a fundamental aspect of Einstein's theory of relativity. Einstein's theory, which revolutionized our understanding of time, posits that the flow of time is affected by gravity and velocity. A striking example of this is the phenomenon known as gravitational time dilation. In the presence of a strong gravitational field like that near a massive object such as a planet or a star, time actually moves slower compared to a region with weaker gravity. This effect, while minute in our everyday life, becomes significant in extreme conditions, such as near a black hole, where gravity is immensely strong. The stronger the gravitational pull, the slower time moves. Velocity also plays a role in how time is experienced. According to Einstein's special theory of relativity, as an object moves faster, time for that object slows down relative to an observer at rest. This effect, known as time dilation due to velocity, becomes noticeable only at speeds approaching the speed of light. For instance, astronauts aboard a spacecraft moving at extremely high speeds would age slightly slower than people on Earth. This isn't just a theoretical prediction, it has been confirmed through experiments, such as observing the decay rates of fast-moving particles and comparing clocks on fast-moving aircraft with those on the ground. These phenomena illustrate that time does not move at a uniform rate throughout the universe. Instead, its flow is malleable, influenced by factors like gravity and speed. This realization has profound implications for our understanding of the universe. It challenges the notion of absolute time, a universal clock ticking at the same rate for everyone, everywhere, and replaces it with a more dynamic view where time is intertwined with the fabric of space itself. The question of whether time can ever move backward is a subject that has intrigued scientists and philosophers alike. In our everyday experience, time seems to move in only one direction, forward. This unidirectional flow of time is so fundamental to our perception of reality that the idea of time moving backward feels like the stuff of science fiction. However, when we delve into the realms of physics and cosmology, the answer becomes less clear and more fascinating. From a classical physics standpoint, the idea of time moving backward is not supported. The laws of classical mechanics that govern everyday objects are time asymmetric, meaning they only work in one direction. This asymmetry aligns with our observation of the arrow of time, where events occur in a sequence from past to future, and processes like aging or the cooling of a hot object seem irreversible. In the world of quantum mechanics, however, the rules are not so straightforward. Many of the fundamental equations in quantum mechanics are time-symmetric. They theoretically work the same whether time is moving forward or backward. This symmetry suggests that, at a microscopic level, the possibility of time reversal cannot be completely ruled out. However, this doesn't mean we can expect to see time-reversed events in our daily lives. The macroscopic world, governed by the second law of thermodynamics, ensures that processes like breaking a glass or spilling coffee don't spontaneously reverse. The concept of time reversal also appears in certain advanced physical theories and hypothetical scenarios. For instance, in the concept of a closed time-like curve predicted by general relativity under specific conditions, it's theoretically possible for an object to return to its own past. However, these scenarios often involve extreme and speculative conditions, like the presence of wormholes or cosmic strings, and remain firmly within the realm of theoretical physics. Moreover, the idea of time moving backward raises profound questions about causality, the relationship between cause and effect. If time could move backward, the basic causal structure of our universe, where causes precede effects, would be undermined. This would not only challenge our understanding of physics, but also our very conception of reality. What are the theories explaining why time moves forward? The theories explaining why time moves forward are grounded in both physics and cosmology, offering various perspectives on this fundamental aspect of our universe. One of the central theories revolves around the second law of thermodynamics, which states that in an isolated system, entropy, a measure of disorder or randomness, tends to increase over time. This increasing entropy gives direction to time, creating what we perceive as the arrow of time pointing from the past to the future. According to this law, processes in nature generally move from states of order to states of disorder. For example, when a building crumbles over time or a hot cup of coffee cools down, these processes are moving towards increased entropy. This increase is statistically more likely than a decrease in entropy, such as the spontaneous assembly of a broken building or a cold cup of coffee heating up on its own. It's this statistical likelihood that gives time its forward direction, making it highly improbable, though not impossible in a theoretical sense, for time to reverse. Another theory that attempts to explain the forward motion of time is related to the conditions at the beginning of the universe. The Big Bang theory posits that the universe started in a state of extremely low entropy. Since then, the entropy of the universe has been increasing, defining the direction of time. This initial low entropy condition of the universe is somewhat of a mystery and a subject of ongoing research and debate. Why the universe started with such low entropy and why it follows a trajectory of increasing disorder are questions that continue to intrigue scientists. In the realm of quantum mechanics, the explanation for time's forward movement becomes more nuanced. Quantum mechanics, in many of its interpretations, allows for time symmetry. Yet in the macroscopic world, we observe a clear arrow of time. Some physicists propose that the act of measurement in quantum mechanics, where a quantum system is observed and defined, may play a role in creating the arrow of time. When a quantum system is measured, it chooses a state from multiple possibilities, a process that could contribute to the unidirectional flow of time as experienced in our daily lives. There's also the theory of cosmological time, which links the direction of time to the expansion of the universe. As the universe expands, it evolves, moving from a highly ordered initial state to a more disordered state. This expansion is tied to the flow of time, suggesting that if the universe were to begin contracting, the arrow of time might reverse, a scenario that is more theoretical than practical in the current understanding of cosmology. Entropy's relationship with time's direction is a key concept in understanding why we experience time moving forward. Entropy, often explained as a measure of disorder or randomness in a system, is central to the second law of thermodynamics. This law states that in an isolated system, entropy tends to increase over time. This increase in entropy is what gives us the arrow of time, the sense that time moves from the past to the future. To illustrate how entropy relates to time's direction, consider a simple example: a box containing a mixture of gases. Initially, if the gases are separated, with one type of gas on each side of the box, the system is in a state of low entropy, meaning it's highly ordered. Over time, these gases will naturally mix, leading to a state of higher entropy or greater disorder. Once mixed, it's extremely unlikely that the gases will separate again into their original state on their own. This one-way progression from a state of low entropy to high entropy mirrors how we experience time moving from past to future. The link between entropy and time's direction also plays a critical role in our understanding of the universe's history. The Big Bang theory suggests that the universe began in a state of extremely low entropy. Since that moment, the entropy of the universe has been increasing, providing a temporal direction from the highly ordered early universe to the more disordered current universe. This cosmic increase in entropy helps explain why we remember the past but not the future, and why cause and effect seem to operate in one direction. In everyday life, the increasing entropy principle is evident in numerous phenomena. From the cooling of a cup of coffee to the rusting of iron, these processes all move towards a state of higher entropy and are irreversible under normal conditions. This irreversibility is a macroscopic manifestation of time's arrow. However, it's important to note that the entropy-time relationship is not as straightforward in all contexts. In the microscopic realm of quantum mechanics, the fundamental laws are mostly time-symmetric, meaning they don't inherently favor a direction of time. This raises intriguing questions about why the macroscopic world, built upon these microscopic laws, exhibits a clear direction of time. Time dilation, a fascinating concept from Einstein's theory of relativity, describes how time is not a fixed experience but can vary depending on speed and gravity. This theory fundamentally changed our understanding of how time works, moving away from the notion of a universal clock ticking at the same rate for everyone, everywhere. In simple terms, time dilation means that time can pass at different rates in different situations. There are two key scenarios where time dilation becomes significant: near massive objects where gravity is strong, gravitational time dilation, and at very high speeds, relativistic time dilation. First, let's look at gravitational time dilation. According to Einstein's general theory of relativity, time moves slower in stronger gravitational fields. This is because gravity can bend space-time, and the closer you are to a massive object, like a planet or a star, the more space-time is curved. For instance, a clock on the surface of the Earth, where gravity is stronger, will tick more slowly compared to a clock on a high-flying airplane. This effect, although minuscule in everyday life, is measurable and has practical implications, like in the operation of the GPS system, where satellite clocks account for these differences to provide accurate positioning. The second type, relativistic time dilation, occurs at high speeds, as described in Einstein's special theory of relativity. If an object moves at speeds close to the speed of light, time will pass slower for it compared to an observer at rest. For example, if you were aboard a spacecraft traveling near light speed and then returned to Earth, you would find that less time has passed for you compared to those who stayed on Earth. This scenario, often popularized in science fiction as the twin paradox, has been experimentally validated using precise atomic clocks on fast-moving aircraft and in particle accelerators. The implications of time dilation are profound. It shows that time is a flexible concept, influenced by factors like velocity and gravity. This flexibility challenges our everyday understanding of time as a constant and uniform flow, revealing a universe much more intriguing and dynamic. The role of time in the Big Bang Theory is pivotal in understanding the evolution of the universe. The Big Bang Theory, which is the leading explanation for how the universe began, posits that the universe started from an extremely hot, dense state, approximately 13.8 billion years ago, and has been expanding ever since. In this context, time is a crucial dimension that charts the history and development of the universe. At the very beginning, in the first moments after the Big Bang, time played a critical role in shaping the universe. According to the theory, as time progressed from that initial moment, the universe cooled and expanded, leading to the formation of fundamental particles and eventually atoms. This cooling and expansion over time allowed for the formation of stars, galaxies, and other cosmic structures. One of the most significant aspects of time in the Big Bang Theory is its relation to the cosmic timeline. This timeline details key events in the history of the universe. For example, roughly 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms, a period known as recombination. This event is crucial because it allowed photons or light particles to travel freely through space, leading to the cosmic microwave background radiation that we can still observe today. Another critical role of time in this theory is in understanding the rate of the universe's expansion. By measuring how fast galaxies are moving away from each other, astronomers can work backward to estimate when the universe began, leading to the current estimate of 13.8 billion years. This expansion is not static, but changes over time, influenced by factors like dark energy, a mysterious force that is causing the expansion rate of the universe to accelerate. Time is also essential in the Big Bang Theory when considering the future of the universe. Based on current understanding, the universe may continue to expand indefinitely, leading to a scenario known as the heat death of the universe, where it becomes so expanded that it cools to near absolute zero temperature, with all processes coming to a halt. Now, how do black holes affect our understanding of time? These cosmic phenomena, formed from the remnants of massive stars, warp space-time to such an extent that they alter the flow of time near them, offering a unique perspective on how gravity influences time. At the edge of a black hole lies the event horizon, a boundary beyond which nothing, not even light, can escape. The gravitational pull near a black hole is so strong that it significantly slows down time relative to an observer far away from the black hole. This effect, known as gravitational time dilation, is a direct result of Einstein's theory of general relativity, which states that massive objects like black holes can warp the fabric of space-time. As a result, time near a black hole passes much slower than time far away from it. For instance, if a clock were to approach the event horizon of a black hole, an observer far away would see the clock ticking slower and slower, eventually appearing to stop as it reaches the horizon. This phenomenon has intriguing implications. For example, if an astronaut were to orbit near a black hole and then return to Earth, they would find that less time has passed for them compared to those who remained on Earth. This is not just a theoretical scenario, it's a practical demonstration of how gravity can affect the flow of time, albeit on a much more extreme scale than we experience in our daily lives. Black holes also challenge our understanding of time in more speculative ways. Some theories propose that the intense gravitational forces of a black hole could warp space-time so dramatically that they create bridges, known as wormholes, to different points in space and time. While wormholes are purely theoretical at this point, and the subject of much debate, they present fascinating possibilities about the nature of time and space. Moreover, the study of black holes has led to questions about the ultimate fate of information and matter that fall into them. This has implications for our understanding of time and the laws of physics, particularly the principle of the conservation of information. The question of whether information that enters a black hole is lost forever, the so-called information paradox, has significant implications for the nature of time, causality, and the fundamental workings of the universe. When it comes to testing time's directionality, several experiments and observations in physics have been key in understanding this aspect of time. These experiments delve into the fundamental properties of time and its flow, particularly in relation to entropy and the laws of thermodynamics. One of the most significant types of experiments involves examining the behavior of particles at the quantum level. In these experiments, physicists observe how subatomic particles like electrons and photons interact in both forward and reverse time scenarios. The laws of quantum mechanics, which govern these particles, are mostly time-symmetric, meaning they should theoretically behave the same way whether time is moving forward or backward. Experiments using particle accelerators, for instance, have shown that the fundamental interactions of these particles remain consistent with this symmetry. These findings are critical in understanding time's directionality, as they suggest that at the most fundamental level, the laws of physics may not prefer a forward direction of time. Another area of research focuses on the entropy of closed systems. Experiments involving isolated systems where entropy is measured over time have been crucial in demonstrating the second law of thermodynamics, which states that entropy tends to increase in an isolated system. This increase in entropy is what gives us the arrow of time, pointing from past to future. For example, experiments that observe the diffusion of particles in a fluid or the cooling of a hot object consistently show this increase in entropy, reinforcing the concept of time's arrow. Cosmological observations also play a role in testing time's directionality. Astronomers and physicists study the expansion of the universe, the cosmic microwave background radiation, and the distribution of galaxies to understand how the universe has evolved over time. These observations support the Big Bang theory, which is inherently time-directional, suggesting that the universe started from a highly ordered state and has been becoming more disordered over time. In addition to these, there have been theoretical proposals for more direct tests of time's directionality. For instance, some physicists have suggested experiments that would test the possibility of closed time-like curves, a concept from general relativity that involves time looping back on itself. However, these remain largely in the realm of theoretical physics and have not been realized in practical experiments. Quantum mechanics, with its peculiar and often counterintuitive principles, challenges the concept of linear time in several intriguing ways. In classical physics, time is viewed as a constant and continuous flow, moving inexorably from the past to the future. However, in the quantum realm, the nature of time becomes much more complex and less straightforward. One of the key ways quantum mechanics challenges the concept of linear time is through its fundamental laws and equations, which are largely time-symmetric. This means that the equations governing the behavior of particles at the quantum level work the same whether time is moving forward or backward. In other words, the basic rules of quantum mechanics don't necessarily dictate a preferred direction of time. This symmetry stands in stark contrast to our everyday experience of time, where events seem to unfold in a definite order from cause to effect. Additionally, quantum mechanics introduces the concept of superposition, where particles can exist in multiple states simultaneously until they are observed or measured. This concept blurs the linearity of time, as it implies that until a measurement is made, we cannot definitively say that a system has evolved in a specific way over time. For instance, in the famous thought experiment known as Schrödinger's cat, the cat in a box is considered both alive and dead until the box is opened, a situation that defies the straightforward progression of time from one state to another. Quantum entanglement, another phenomenon in quantum mechanics, also challenges traditional notions of time. When particles are entangled, the state of one particle is directly related to the state of another, regardless of the distance between them. Changes to one particle are instantaneously reflected in the other, suggesting a level of connection that seemingly transcends time and space. This instantaneous nature of entanglement presents a puzzle for the linear cause and effect view of time. Moreover, some interpretations of quantum mechanics, such as the Wheeler-DeWitt equation in quantum cosmology, describe a universe where time as a distinct dimension doesn't exist at all. In these models, time emerges as a property of the universe only under certain conditions, challenging the idea of time as a fundamental backdrop to all physical processes. Now, let's talk a bit about wormholes. Wormholes are a concept in theoretical physics that represent a fascinating intersection of space, time, and gravity. Often described as shortcuts or tunnels through space-time, wormholes have captured the imagination of scientists and science fiction enthusiasts alike. In the realm of physics, a wormhole is a hypothetical bridge or connection between two separate points in space-time, potentially allowing for travel between them that is faster than it would be through normal space. The theory of wormholes comes from Einstein's theory of general relativity, which describes how gravity is the result of the curvature of space-time by mass and energy. Wormholes are solutions to the equations of general relativity. However, it's important to note that they remain theoretical and have not been observed in reality. In terms of their relation to time, wormholes present intriguing possibilities. If they exist, wormholes could theoretically allow for time travel. This is because the theory of relativity allows for the possibility of space-time being curved in such a way that it connects not just two different locations in space, but also two different points in time. In this scenario, traveling through a wormhole could potentially take you to a different time as well as a different location in the universe. However, the concept of time travel via wormholes comes with numerous scientific and philosophical challenges. One major issue is the requirement of exotic matter to keep a wormhole open. Exotic matter is a form of matter that would have negative energy density and negative pressure, something not currently known to exist in the form required. Without this exotic matter, the wormhole would collapse so quickly that nothing could pass through it, making it unusable for travel. Moreover, time travel through wormholes raises paradoxes, the most famous being the grandfather paradox, where a time traveler could potentially prevent their own existence by altering past events. These paradoxes present significant challenges to our understanding of causality and the nature of time. Can we theoretically travel in time? The theoretical possibility of time travel is a topic that has long fascinated both scientists and the public. While the concept often appears in the realm of science fiction, there are aspects of modern physics that suggest time travel could, in theory, be possible, albeit with significant limitations and challenges. The basis for considering time travel lies primarily in Einstein's theory of relativity. According to general relativity, the strong gravitational field of a massive object can warp space-time around it. This warping affects how time passes, a phenomenon known as gravitational time dilation. In theory, if one could orbit near a massive object like a black hole without being pulled in, time would pass slower for them relative to someone far away from the gravitational field. This is a form of time dilation, and while it's not traveling through time in the science fiction sense, it does mean that time can pass at different rates in different parts of the universe. Another theoretical possibility for time travel comes from the concept of wormholes, which are predicted by the equations of general relativity. A wormhole could connect two distant points in space-time, and potentially, if one end of a wormhole is moved in a specific way, it could create a situation where traveling through the wormhole takes you back in time. However, the practical challenges of this are enormous. The creation and maintenance of a wormhole would require exotic matter with negative energy, something that has not been observed in the required form. Moreover, even if such a wormhole could be created, there are questions about its stability and safety for travel. The idea of traveling to the future is theoretically more straightforward than traveling to the past. According to special relativity, if one could travel at speeds close to the speed of light, time would pass slower for them compared to someone at rest, effectively allowing them to jump into the future. However, the technological challenges of achieving such speeds are currently beyond our capabilities. Traveling to the past presents additional problems, not just technologically, but also in terms of physics and causality. The notion of traveling back in time introduces paradoxes, such as the aforementioned grandfather paradox, which challenge our fundamental understanding of cause and effect. Additionally, most physicists believe that the laws of physics are likely to prevent backward time travel to avoid these paradoxes. Now, what is really the end of time according to cosmology? In contemplating the end of time through the lens of cosmology, we delve into a realm where science intersects with the profound mysteries of the universe. One of the most intriguing theories in this regard is the concept of the Big Freeze. This theory, rooted in the principles of thermodynamics and the expanding universe, suggests that as the universe continues to expand, it will gradually cool down. The rate of expansion, influenced by dark energy, a mysterious force that accelerates the universe's growth, plays a critical role in this scenario. The Big Freeze posits a future where stars exhaust their nuclear fuel, leading to a universe devoid of the light and warmth of stars. As galaxies drift apart and stars burn out, the universe will inch closer to absolute zero, the theoretical temperature where all thermal motion ceases. This gradual process, taking place over trillions of years, signifies not just the extinguishing of stars, but the end of all known physical processes that support life and structure in the universe. Accompanying the Big Freeze is the concept of heat death, where entropy, a measure of disorder in a system, reaches its maximum. In such a state, no energy is available to perform work, and the universe attains a state of thermodynamic equilibrium. Everything becomes uniform, with no temperature variations or energy gradients to drive change or enable life as we know it. Another fascinating concept is the Big Rip, which presents a more dramatic end. The Big Rip theory hinges on the behavior of dark energy. If dark energy increases over time, it could tear apart everything from galaxies to atoms. In this scenario, the fabric of space-time itself would be relentlessly stretched until its ultimate demise, leading to a universe where distances between all points become infinite. On a philosophical level, these theories compel us to ponder the nature of time and existence. They remind us that the universe operates on scales and principles far beyond our everyday experiences. Whether through a slow descent into cold darkness or a catastrophic tearing apart, the end of time as hypothesized by cosmology paints a picture of a universe far removed from the vibrant, dynamic cosmos we currently inhabit. Delving into the limitations of our current understanding of time, especially in the context of cosmology and science, takes us on a journey through a complex and often perplexing landscape. Time, a fundamental aspect of our daily lives, becomes increasingly enigmatic when examined through the lens of advanced physics. One of the primary challenges in understanding time is its integration with space in the fabric of space-time, a concept central to Einstein's theory of general relativity. This theory revolutionized our understanding of gravity, showing that massive objects cause a distortion in space-time, which we experience as gravity. However, this intertwining of space and time raises profound questions, particularly about the nature of time itself. In the realm of quantum mechanics, time's treatment contrasts starkly with that in relativity. Quantum theory, governing the behavior of particles at the smallest scales, treats time as a fixed, unchanging background, not as something that is fluid and dynamic as in relativity. This disparity presents a significant conceptual hurdle in physics, often referred to as the problem of time. It is one of the biggest challenges in developing a theory of quantum gravity, a theory that would unify the principles of quantum mechanics with those of general relativity. Our perception of time adds another layer of complexity. Human consciousness experiences time as a continuous flow, but whether this flow mirrors a fundamental property of the universe, or is just a construct of the human mind, is an ongoing debate in both physics and philosophy. Now, let's take a look at the block universe theory. The block universe theory, a concept that has piqued the curiosity of many in the fields of advanced cosmology, science, and philosophy, offers a unique perspective on the nature of time and our universe. This theory, rooted in the principles of Einstein's theory of general relativity, posits that time is just another dimension, much like the three spatial dimensions we are familiar with. In this view, the past, present, and future all coexist equally, and the flow of time we experience is more an aspect of human perception than a physical reality. Imagine the universe as a vast four-dimensional block where all moments in time are laid out alongside each other. This block universe encompasses every event that has ever happened or will happen, from the birth of stars to the most mundane daily occurrences. In this framework, what we perceive as the past is simply a different region of the block universe, just as real and tangible as the present or the future. One of the intriguing implications of the block universe theory is the challenge it poses to our understanding of causality and free will. If the future already exists in this four-dimensional block, it suggests a deterministic universe where future events are fixed and unchangeable. This idea stands in contrast to our usual experience of making choices and influencing future outcomes. It raises profound philosophical questions about the nature of free will and our role in the tapestry of time. Another significant aspect of the block universe theory is its compatibility with the phenomenon of time dilation, a key prediction of relativity. According to relativity, observers moving relative to one another or in different gravitational fields will measure time differently. In the block universe model, these differences in time perception are simply different paths through the four-dimensional space-time continuum. This concept aligns neatly with the experimental evidence supporting time dilation, such as the observed differences in time measured by atomic clocks on Earth and in satellites. Despite its compelling aspects, the block universe theory is not without its skeptics. Some argue that it conflicts with the apparent randomness inherent in quantum mechanics, the branch of physics that deals with subatomic particles. Quantum mechanics suggests a fundamental uncertainty in the behavior of these particles, a feature that seems at odds with a predetermined block universe. Could the universe exist without time? At its core, time is a measure of change. It's the framework within which we understand how events unfold and progress from one moment to the next. In the realm of classical physics, time is a continuous, flowing river, marching forward inexorably. This view aligns with our everyday experiences, where we see cause and effect play out in a linear fashion. However, when we dive into the realms of advanced physics, the nature of time becomes far more complex and elusive. According to Einstein's theory of general relativity, time is intertwined with the three dimensions of space, forming a four-dimensional space-time fabric. This fabric is warped and bent by the mass and energy of objects within it. Here, time is not just a simple backdrop against which events occur, it's an active player in the dynamics of the universe. For example, The second law of thermodynamics, which states that entropy, or disorder, increases over time in an isolated system, is fundamental to our understanding of physical processes. Without time, such principles would lose their meaning, leaving us without the tools to describe or understand the behavior of the universe. Time gives context to our experiences and allows for the concept of causality, the relationship between cause and effect. Without time, the very notions of existence and change become undefined or meaningless. Is time really a measurable unit? If so, what is the smallest unit possible? The smallest measurable unit of time, a topic that fascinates those with a keen interest in advanced cosmology, science, and philosophy, is known as the Planck time. Named after Max Planck, the German physicist who is considered the father of quantum theory, Planck time is a key concept in the realm of theoretical physics. To understand the magnitude of Planck time, one must delve into the world of incredibly small and fast measurements. Planck time is approximately 5.39 x 10 circumflex 44 seconds. This is a time so brief that it's hard to comprehend. It's a duration in which light, the fastest thing in the universe, would travel only a minuscule fraction of the diameter of a proton. This concept emerges from the Planck scale, which is a domain of physics where the effects of both quantum mechanics and general relativity are significant. The Planck scale represents the point at which our conventional understanding of physics starts to break down, and the classical descriptions of gravity and space-time cease to be valid. At the Planck scale, the very fabric of space-time is thought to become quantized, meaning it is composed of discrete, indivisible units, much like the pixels on a digital screen. Planck time is derived from fundamental constants in physics. It is calculated using the gravitational constant, g, which appears in Newton's law of universal gravitation, the speed of light, c, and Planck's constant h, which is crucial in the field of quantum mechanics. These constants are woven together in a formula that gives rise to the Planck time, representing a theoretical limit to measuring time. However, it's important to note that Planck time is not something we can measure directly with current technology. Instead, it is a concept used by physicists to understand the universe at its most fundamental level. In practical terms, the smallest increments of time we can currently measure are many orders of magnitude larger than Planck time. The most precise atomic clocks, for instance, can measure time changes in the order of attoseconds, which is 10 circumflex 18 seconds, still vastly longer than Planck time. As we consider the incredibly small scale of Planck time in the universe, it naturally leads us to ponder how fundamental particles interact with this most elusive dimension, time. This question lies at the heart of some of the most profound and complex areas of cosmology and physics, and is particularly intriguing when we explore the behavior of the smallest constituents of matter. Fundamental particles such as quarks and leptons, which include electrons and neutrinos, are the building blocks of the universe. Their interactions with time, especially at quantum levels, defy our everyday notions of how objects should behave. In the world of quantum mechanics, particles do not experience time in the linear, straightforward way that we do. Instead, their behavior is governed by probabilities and uncertainties. One of the key principles in quantum mechanics is the Heisenberg uncertainty principle. It states that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. Intriguingly, there is a similar relationship between energy and time. This means that at very small time scales, like those approaching Planck time, there is a fundamental limit to the precision with which we can measure the energy of a particle. This uncertainty in energy can lead to some counterintuitive phenomena, such as the temporary creation of particle-antiparticle pairs from the vacuum of space, known as virtual particles. These particles exist for incredibly short periods of time, in accordance with the uncertainty principle. Furthermore, in the realm of particle physics, the concept of time reversal is a fascinating aspect. Under certain conditions, the fundamental equations governing the behavior of particles remain valid if time is reversed. This symmetry, known as T-symmetry or time reversal symmetry, suggests that on a fundamental level, the laws of physics could operate the same way whether time moves forward or backward. However, in the macroscopic world, we do not observe this symmetry due to the second law of thermodynamics, which dictates that entropy, or disorder, tends to increase over time, giving a direction to the arrow of time. Continuing from our exploration of how fundamental particles interact with time, particularly the concept of time reversal or T-symmetry in physics, we find ourselves delving into the broader implications of time symmetry in the physical world. Time symmetry, or the idea that the fundamental laws of physics are the same whether time moves forward or backward, presents intriguing consequences for our understanding of the universe. In theoretical physics, time symmetry implies that a particle moving forward in time should behave in the same way as if it were moving backward. This is more than a mere scientific curiosity. It's a principle that plays a crucial role in various physical theories and models. For instance, many equations in quantum mechanics and classical mechanics are time-symmetric, meaning they would still be valid if time were to flow in reverse. However, the observable universe doesn't seem to exhibit this symmetry in practice. We experience time as moving in a single direction, from past to future. This asymmetry is most notably encapsulated in the second law of thermodynamics, which states that the total entropy, disorder, of an isolated system can never decrease over time. This gives us the arrow of time, pointing from a less to a more disordered state. One of the profound implications of time symmetry in physics is the possibility that at fundamental levels, the universe doesn't have a preferred direction of time. This notion challenges our everyday experiences and raises questions about the nature of time itself. Could the forward flow of time be a feature of our perception rather than a fundamental property of the universe? Another significant implication of time symmetry is its role in theoretical models and experiments. In particle physics, particularly in the study of subatomic particles using large colliders like the Large Hadron Collider, LHC, time symmetry is an essential aspect of understanding particle interactions. Experiments often test the time reversal symmetry of certain processes to probe deeper into the fundamental forces and particles that make up our universe. Moreover, the concept of time symmetry has led to speculative but fascinating ideas in cosmology. For example, some theories suggest the possibility of a universe where time did run in reverse before the Big Bang. While these ideas are highly theoretical and not without controversy, they illustrate the rich tapestry of possibilities that time symmetry opens up in our quest to understand the cosmos. Now, let's delve back into the question of this video. Why does time move forward? Could it be an illusion? Exploring whether the forward movement of time is an illusion takes us further into the intriguing complexities of physics and philosophy. This question ties into the earlier discussion about time symmetry and the arrow of time, which is central to our understanding of the universe and our place in it. The perception that time moves inexorably forward is a fundamental aspect of human experience. We remember the past, but not the future. We grow older, not younger. This unidirectional experience of time is so ingrained in our daily lives that the idea of it being an illusion seems almost unfathomable. However, when we delve into the realms of advanced physics, the certainty of this forward movement begins to blur. At the heart of this debate is the nature of time itself. In classical physics, time is seen as a constant, ever-flowing river, moving from the past, through the present, and into the future. This view aligns with our everyday experiences and the macroscopic world around us. However, as we've seen in discussions of time symmetry in physics, the laws that govern the behavior of fundamental particles at the quantum level don't necessarily distinguish between past and future. These laws are symmetric with respect to time, suggesting that, at a fundamental level, the forward flow of time may not be an inherent aspect of the universe. This leads to the philosophical and scientific consideration that our perception of time moving forward could be a result of human consciousness or the way our brains process information, rather than a fundamental property of time itself. This idea is further supported by the second law of thermodynamics, which states that entropy, or disorder, in an isolated system tends to increase over time. This increasing disorder gives us the impression of a forward-moving arrow of time, but it doesn't necessarily mean that time itself has a direction. Some theorists have proposed that the universe at its most basic level might be time-symmetric, with no preferential direction. In such a scenario, the forward movement of time that we experience could be more of an emergent phenomenon, arising from the laws of thermodynamics and the initial conditions of the universe, rather than from the fabric of time itself. Building on our exploration of whether the forward movement of time is an illusion, we naturally segue into the fascinating interplay between consciousness and time perception. This aspect touches upon how our minds comprehend and interpret the passage of time, a topic that delicately balances on the border between science and philosophy. Consciousness, the state of being aware of and able to think about one's own existence, greatly influences how we perceive time. Our subjective experience of time can vary dramatically from the objective measurement of clocks and calendars. For instance, we've all experienced moments where time seems to fly by when we're engaged in enjoyable activities, or conversely, drags on when we're bored or anxious. This phenomenon indicates that our perception of time is not a constant stream, but is malleable and influenced by our mental state and activities. Neuroscience has begun to unravel some of the mysteries behind this. Studies have shown that different areas of the brain are involved in processing time, and our perception of time can be affected by various factors including attention, memory, emotions, and even neurological disorders. For instance, when we're focused on a task, our brain might process more information per unit of time, making it seem like time is passing more slowly. The relativity of time perception is also evident in life-threatening situations. Many report experiencing these moments in slow motion. This could be due to the brain switching into a high alert mode, processing information at an accelerated rate to help us react more quickly to the danger. However, interestingly, studies suggest that this is more about how we remember the event rather than how we experience it in real time. The brain records more detail during these intense moments, leading to a perception of extended time when we recall the event. Philosophically, the link between consciousness and time perception raises profound questions about the nature of reality. If our perception of time can be so easily influenced by our mental state, to what extent is the passage of time an objective feature of the universe versus a construct of human consciousness? Moving from the intriguing relationship between consciousness and time perception, we find ourselves naturally drawn to the role of memory in shaping our experience of time. Memory, an integral aspect of our consciousness, has a profound impact on how we perceive the passage of time, intertwining with our subjective sense of duration and the chronological sequence of events. Memory allows us to store and recall past experiences, essentially creating a personal timeline of our lives. This mental timeline is fundamental to our perception of time. How we remember events can significantly influence our sense of how much time has passed. For example, when we recall a period filled with varied and new experiences, it may seem longer in retrospect. This is often why, when looking back, time spent on a vacation or learning a new skill can feel more extended than a similar duration spent in routine or mundane activities. The richness and variety of experiences seem to stretch time in our memory. This phenomenon, known as the holiday paradox, illustrates how dense memories, full of new experiences, can make a period seem longer when we reflect on it. In contrast, periods with fewer new memories might seem to have passed more quickly, despite occupying the same amount of actual time. Additionally, the emotional content of memories plays a significant role in our perception of time. Emotionally charged events, be they joyful, traumatic, or sorrowful, are often more vividly remembered. This vividness can make these periods seem to last longer in our minds. It's a common experience that time feels like it's dragging during challenging or painful moments and flies by during happy times. Age also affects how we perceive time through memory. As we grow older, the rate at which we form new memories tends to slow down. This can make time seem to speed up as we age, because fewer new memories might be created over a given period compared to when we were younger. Childhood and young adulthood often feel like longer periods because they are times of numerous first experiences and significant changes, all of which create dense, rich memories. Furthermore, the way we recall memories is not always linear. We often remember events out of sequence, and our perception of time can be influenced by how frequently we recall certain memories. The more often we think about a particular event, the more significant and extended it may seem in our mental timeline. Animals, much like humans, experience time, but their perception of it can be markedly different, influenced by various factors including their size, metabolic rate, and ecological needs. For instance, smaller animals with faster metabolic rates like birds and insects often perceive time in finer slices. This means they can process visual information more rapidly than larger animals, allowing them to react to their environment more quickly. A famous example is the fly, which can see and react to movements much faster than a human can, making it seem like it has lightning-fast reflexes. Studies have shown that this difference in time perception is linked to the animal's nervous systems. The speed at which an animal's nervous system processes information affects how it perceives the passage of time. For instance, animals that need to escape from predators or catch fast-moving prey have evolved to process information at an accelerated rate, which may make time seem to pass more slowly to them. The lifespan of an animal also plays a role in how it perceives time. For animals with shorter lifespans, like a mouse, a year is a significant portion of its life, whereas for humans, a year is a much smaller fraction. This difference in lifespan can affect how animals perceive shorter intervals of time. An event that seems brief to a human might seem much longer to an animal with a shorter lifespan. Moreover, the way animals perceive time can influence their behavior and survival strategies. Migratory birds, for example, follow seasonal cues for migration, which are tied to changes in daylight length over the year. This indicates an awareness of longer temporal cycles, essential for their survival. Interestingly, some animals exhibit behaviors that suggest an understanding of future events, a concept closely tied to time perception. For instance, squirrels store food for the winter, and some primates have been observed using tools in ways that indicate planning for future needs. These behaviors imply a mental representation of future time, although it's not clear if this is based on a conscious understanding of time as humans experience it. Linking the concept of time perception in animals to the broader topic of how time affects aging and lifespan brings us to a captivating intersection of biology, physics, and philosophy. Aging, a process experienced by all living organisms, is intrinsically tied to the passage of time, and understanding this relationship can shed light on the very nature of life and longevity. At the most fundamental level, aging can be seen as the accumulation of time's effects on biological systems. Over time, cells in an organism accumulate damage due to a variety of factors, including environmental stresses, genetic factors, and the natural limits of cellular replication. This damage accumulates, leading to the gradual decline in physiological functions that we associate with aging. The rate of aging and the lifespan of an organism are influenced by a complex interplay of genetic and environmental factors. For instance, smaller animals like mice have a faster metabolism and generally live shorter lives, while larger animals like elephants have slower metabolisms and longer lifespans. This observation has led to the rate of living theory, which suggests that an organism's lifespan is related to its metabolic rate. However, this theory doesn't fully explain the variations in lifespan among different species, as there are many exceptions to this pattern. On a cellular level, the concept of telomeres plays a crucial role in aging. Telomeres are protective caps at the ends of chromosomes that shorten with each cell division. Once telomeres reach a critically short length, cells can no longer divide and become senescent or die, a process that contributes to aging. Interestingly, some species have ways to maintain their telomeres, leading to longer lifespans. For example, lobsters produce an enzyme called telomerase, which repairs their telomeres, potentially giving them a longer lifespan. Furthermore, the field of gerontology, which studies aging, has identified various genetic factors that influence lifespan. Some species, such as certain strains of laboratory worms and mice, have been shown to live significantly longer or shorter lives based on specific genetic mutations. These findings suggest that the genetic makeup of an organism plays a significant role in determining its lifespan. In humans, aging is a complex process influenced not only by genetics, but also by lifestyle factors such as diet, exercise, and exposure to toxins. These factors can affect the rate at which cellular damage accumulates over time, influencing overall health and longevity. As we reflect on how time affects us humans and other living creatures, what has been some scientific breakthroughs that have altered our understanding of time? Have there been any? In the journey to understand time and its intricacies, various scientific breakthroughs have significantly altered our comprehension of this fundamental aspect of the universe. These milestones span across centuries, each contributing to a deeper and more nuanced understanding of time. One of the earliest and most significant breakthroughs was Isaac Newton's formulation of his laws of motion and universal gravitation in the 17th century. Newton's work laid the foundation for classical mechanics, in which time was viewed as a constant and absolute entity, flowing uniformly and unaffected by the motion of objects or the observer. This view of time as a separate, independent dimension was the bedrock of physics for centuries. However, the most revolutionary shift in our understanding of time came with Albert Einstein's theory of relativity in the early 20th century. Einstein's theory, which includes the special theory of relativity, 1905, and the general theory of relativity, 1915, brought about a profound change in how time is perceived. The special theory of relativity introduced the concept that time is relative, meaning it can vary for different observers depending on their motion. This theory also led to the famous equation E clutch mc2, which links energy, E, mass, m, and the speed of light, c, and has far-reaching implications in both physics and cosmology. Einstein's general theory of relativity further revolutionized our understanding by showing that time is intertwined with space, forming the four-dimensional space-time continuum. This theory demonstrated that massive objects cause a curvature in space-time, which we perceive as gravity. These concepts were groundbreaking, depicting time not as a fixed, flowing river, but as a dimension that is affected by gravity and the observer's velocity. Another significant breakthrough came with the development of quantum mechanics in the 20th century. Quantum mechanics deals with the behavior of particles at the smallest scales, where the classical laws of physics do not always apply. In quantum mechanics, time is treated as a background parameter, not as a variable that can change. This treatment of time differs from that in relativity, leading to ongoing efforts to reconcile the two theories in a unified framework. The advent of highly precise atomic clocks in the 1950s also greatly enhanced our understanding of time. These clocks, which use the vibrations of atoms to measure time, have allowed scientists to test the predictions of relativity with remarkable accuracy. For instance, experiments using atomic clocks have confirmed the time dilation effects predicted by relativity, such as time passing at different rates at different altitudes due to the influence of gravity. Furthermore, the discovery and study of cosmic microwave background radiation in the 1960s have provided insights into the age and evolution of the universe, offering a window into the very early stages of time after the Big Bang. As we near the end of our journey, let's take a step back and reflect on everything. What would a world without time look like? Time is such an integral part of our existence that envisioning a world devoid of it is both fascinating and complex. In a world without time, the most fundamental change would be the absence of change itself. Time allows for the progression of events, for causes to lead to effects, for the unfolding of life and the evolution of the universe. Without time, everything would be static and unchanging. There would be no growth, no decay, no motion, and no evolution. The dynamic processes that define life and the universe as we know it, such as the birth and death of stars, the formation of galaxies, and the very cycle of life on Earth, would be impossible. From a physical standpoint, the laws of physics as we understand them would be fundamentally different in a world without time. The equations that describe motion, energy, and gravity rely on time as a critical variable. Without time, these concepts would lose their meaning. For example, velocity becomes an irrelevant concept if there is no time to measure the change in position. In terms of human experience, a world without time would mean an absence of history, memory, and anticipation. Our entire understanding of existence is built around past experiences, present moments, and future expectations. In a timeless realm, there would be no aging or development. We wouldn't experience life as a series of events or progressions. Concepts like rhythm, routine, deadlines, and schedules would be meaningless. Moreover, many philosophical and existential questions arise in a world without time. For instance, without the progression of time, would concepts like purpose, achievement, and progress hold any meaning? Our goals, aspirations, and motivations are deeply tied to the passage of time and the ability to effect change. In a timeless state, these driving forces of human behavior and society would be irrelevant. The absence of time would also mean that the universe is unchanging and eternal in its current state. This contradicts our current understanding of the universe, which is based on the principles of change and evolution over time, from the Big Bang to the present day. Continuing our reflecting of time, particularly the idea of a world without it, naturally leads us to ponder what future research is necessary to deepen our understanding of time. Time, being one of the most fundamental yet enigmatic components of the universe, remains a subject of intense study and curiosity in various scientific fields. One key area of future research involves the quest to reconcile the two pillars of modern physics: general relativity and quantum mechanics. General relativity, Einstein's theory that describes gravity as the warping of space-time by mass and energy, treats time as a smooth continuum. On the other hand, quantum mechanics, which governs the realm of the very small, like atoms and subatomic particles, treats time as a background parameter separate from the quantum states of matter. These differing views on time have led to a significant theoretical impasse. A major goal in physics is to develop a theory of quantum gravity that can integrate these two frameworks, potentially leading to new insights into the nature of time. Another important area of research is the study of the early universe. By examining the conditions shortly after the Big Bang, scientists hope to understand how time emerged and evolved. This involves studying cosmic microwave background radiation, the afterglow of the Big Bang, and detecting and analyzing gravitational waves, ripples in space-time caused by cataclysmic events in the distant universe. These studies could provide crucial clues about the nature of time in extreme conditions. Advancements in technology, particularly in the precision of time measurement, are also vital. Atomic clocks, which use the vibrations of atoms to measure time, have revolutionized our ability to measure time with incredible accuracy. Future developments in atomic clocks and other time-measuring devices could allow for even more precise experiments, testing the predictions of relativity and quantum mechanics at unprecedented levels. Research into black holes and their event horizons also offers a promising avenue for understanding time. Black holes, with their immense gravity capable of significantly bending space-time, provide natural laboratories for studying the extreme effects of gravity on time. The event horizon of a black hole, the point beyond which nothing can escape, poses fascinating questions about the nature of time, space, and matter. In addition to physical studies, interdisciplinary research involving neuroscience and psychology is important to understand how humans perceive and experience time. This research could lead to insights into the relationship between the brain, consciousness, and time perception. Finally, advancements in cosmology. Through the study of the universe's expansion and the behavior of dark energy and dark matter, could shed light on the future of the universe and the role time will play in its ultimate fate. As we draw our exploration of time to a close, we reflect on the vast and complex tapestry of ideas, theories, and discoveries that weave together our understanding of this most fundamental aspect of the universe. From the earliest observations of celestial bodies to the cutting-edge theories in physics, the journey through time has been a journey through the very heart of existence and reality. We've seen how time, once thought to be unchanging and absolute, has revealed itself to be fluid, relative, and deeply intertwined with the fabric of space. Einstein's revolutionary ideas on relativity have opened our eyes to a universe where time bends and stretches, challenging our deepest intuitions. The enigmatic nature of quantum mechanics has added layers of complexity, showing us a world where time may not even hold sway at the smallest scales. In the end, time is not just a dimension to be studied, it is a narrative to be lived, a challenge to be understood, and a mystery to be pondered. As we stand at the frontier of knowledge, looking out into the cosmos, we are reminded of our small but significant place in the vast expanse of space and time. This journey through time, from the cosmic to the quantum, from the philosophical to the practical, continues to inspire, challenge, and awe. It is a journey that, much like time itself, has no end, only the promise of new beginnings and deeper understandings. Thanks for watching, and make sure to subscribe to our channel Space Dust for more videos like this.